Hi everyone, my name is Gijs Besson. I'm one of the developers of iMat, and I'm excited to share all the new developments around the FLAG3D OpenPit module for iMat. I won't have time today to cover all the features in iMat. The majority of today's focus will be around the OpenPit module, but I will touch on some of the other plugins as in iMat. Let's get started. I'm going to start by creating a new iMat project and selecting the new iMat project option. I'll give it a project name. I'll call this my pit. I'll just store it in the default location, and I'll just call my name pit. The reference system, X increasing east, Y increasing north, and Z increasing up, and length is measured in meters. I'll just say OK, and done. On the left-hand side, for those of you that are familiar with iMat, we have the Project Explorer window. All the items highlighted in bold are known as plugins to iMat. And depending on which license features you've purchased with your version of iMat, several of these options may or may not be there for you. However, these are all the options that we currently have available. The Geometries plugin is a plugin used to manage all geometries in iMat. We can import several different kinds of geometries. For example, if I just select the Geometries plugin, and the information window shows you which geometries we support. So we've got STL, DXF, DWG, STR and DTM formats that's used by SURPAC, and then a few internal iMat formats, lines, points, and grids, and then also map3D input files that we can import here. The Geometries plugin is mainly used to visualize geometries in iMat, and it's also used to clean up some very bad meshes. So for those of you that used Rhino in the past, several Rhino functionalities have made its way into iMat simply to help users to clean up meshes for modeling if required. The Spatials plugin is used to create spatial volumes to filter for example, any field data, such as seismic data or borehole data or block model data, as well as numerical modeling data. We'll be using some spatials today when we create our OpenPit project. So you'll see how those will be used. The block models plugin allows users to import block models of various material parameters, to render them, as well as to assign those material parameters to your FLAG3D projects. Then we've got the two FLAG3D modules, the underground and the OpenPit. So the underground module was the one that we released first and has been used quite extensively. The underground plugin is mainly used for underground modeling examples. That means stoping, caving, most of those underground operations, but you also have the flexibility of adding pits. The main difference between the OpenPit and the underground plugin is that the OpenPit module is mostly focused on open pits and slope stability, whereas underground doesn't focus on slope stability as much. And the second thing is that the OpenPit module allows you to use water in your model. So it includes spore pressures in the numerical model, whereas the underground plugin doesn't allow for that. We'll be spending most of our time today using this OpenPit plugin. There's also the charts plugin that allows you to create various charts, whether it being time-based or seismic-based. So, for example, time plots, Gutenberg-Richter plots, Stereonet plots, for those of you that are familiar with all these names. The two seismic plugins, the Seismic Data and Seismic System plugin, are the two plugins used for seismic data analysis and can be combined with synthetic seismicity that's extracted from our numerical model. So if you are using the underground plugin, you can extract synthetic seismicity from those models and compare it to real seismicity that's recorded by your seismic system. And then the two final plugins, the borehole plugins and the Movie Makers plugins. The borehole plugins or drill hole plugin allows you to import different field data that's measured in drill holes and render those and use it together with your numerical models. And the Movie Makers plugins allows you to do screen recordings and compile it into AVI or MP4 formats so that you can use it in presentations. All right, so let's get started. I'll just select my file explorer And I'll drag this over onto the screen just to show you what we've got to use today to build our model. So if I go into the geometries folder, for this particular mine, I've got several lithologies. I've got 5 different pit shell geometries. These are STL files. I've got several structures, and I've got a water table for also representing the 5 different steps. So I'm going to be building a model with 5 different steps, starting in step 1, ending in step 5, importing 5 pit shells for those steps, as well as the water table geometries for those steps. Let's get started. I'll select all of these to import them into iMat. There's a few different ways you can do this. You can right-click on the geometries plugin, and you can import all of these geometries, or you can import them one by one. I simply like the drag and drop option, where you drag and drop them onto the geometries plugin and it imports directly. Before it imports, basically every single importer in iMat allows you to convert the data file. So it's often a case in mines where the geometries and field data that we work with lives in a different coordinate system or are offset to the current project that we have. This gives you the option before import to convert those. In this example, I'm not going to convert any data. I'm simply going ahead and selecting OK, and that's imported. Now you can already see I've imported 9 structures, 5 water table items, 5 pit shell items, and 1 lithology. If I turn on the first pit shell, we'll get an idea of what the model is that we're going to build. So this is quite large. Well, the first pit shell actually has no pit. It's just a free surface with some mountain range here on the eastern side. If I go into a plan view, we can see that it's, well, this geometry is actually quite large. So we're approximately 6.6 kilometers well, actually even a little bit more, almost 8 kilometers across in this section, and approximately 8 kilometers in this section as well. So it is an extremely large model. What I'll do is I'll turn on the final pit shell so we can actually see where this pit exists within the current free surface. You can see that the area that we're going to be focusing on is mainly this area over here, sort of towards the west side of this mountain range here. So we'll be using this information and most likely making our model slightly smaller, not including the entire free surface. I'll just turn on the water table as well for reference. So if I look at the water table geometries that we have, so it's actually quite rough, and it does even in certain places intersect the free surface. That's for step 1. And if I do the same, I'll just turn the final pit shell on. Look at the final water table location. This one is actually a lot better, although we've got some strange shapes here in the bottom part there, which may be artificial. So our job would be to clean this up before we can actually build a model. However, the tools that I'm going to be showing you today will clean this up automatically in iMat for you. So you don't have to clean this up. And just while we're on the subject of cleaning up geometry, so if we look at this final pit shell shape, this is probably one of the worst pit shell shapes that exist. So we can see that this wireframe is not nicely closed. We've got some holes in this wireframe. This is typically a problem. When we do numerical modeling, we don't want these artifacts. And then the pit shell is not even complete for the final stage. We've got some holes in here. Maybe if I turn on the previous pit shell, we can see it does merge up nicely, but even this shape isn't perfectly perfect for our modeling purposes. So in the past, if you were to build all of this, or were to build a model of these pit shells, you would have to clean up for each stage these wireframes in softwares like Rhino before you can build models. However, again, as I mentioned, the tools that I'm going to be showing you today, it cleans it up automatically for you. Effectively, what iMat will do for you automatically is remodel, or basically what we call it, redrape the pit shells so that you don't have to do it, saving you a lot of time. So let's get started. So we've got an idea what the geometries look like now. I'm going to jump straight into the FLAC3D Open Pit plugin, and I'm going to create a new FLAC3D project. I'll call this example hook brown. So I'm going to be using a hook brown material to represent this this pit. Let's say OK. And while I'm creating this FLAC3D project, I just want to mention that you're not restricted to just a single flag 3D project. In iMat, you can create as many as you like. So a good example is if you have a calibration that you want to perform, test different stress states or different material properties for exactly the same model. You're not limited to one flag 3D project. You can create 10 or 100 different versions if you like in here. Now, I've just typed in the flag 3D project name, and the next step in the process is to choose my pore pressure input. And you've got a few different pore pressure modes that we do support. The first mode is basically self-explanatory. If we don't want to include pore water in our model, we can select the none option, and there's a short description below here. We can see what this option does. The next option is a fixed elevation. So we can assume that the pore pressure or the water table in our model remains at a fixed elevation for all mining stages. So we've got the option to enter some Z coordinate or an elevation at which the water table exists. Next option is a depth below surface option. So we can type in a value for a certain elevation, let's say, for example, 500 meters. And what will happen is for every single stage, the water table will exist exactly 500 meters below the surface. So it changes with your mining excavation. Another option is the water table geometries option. And this is the option that we'll be using today. We'll be importing wireframes of where the water table locates. And then the final option is the MineDW grid. This is basically our MineD watering software. It produces almost a block model-like grid where pore pressures are defined for every vertex on the grid. So for those of you that use the MineDW option, you can import those MineDW grids directly into iMat and use those pore pressures. That's basically output from the software. But as mentioned, we're going to use this option today. We're going to use wireframes that defines the water table for each stage. I'll select that and select OK. And this has created a new flag 3D open pit project. If I expand this, you'll see that the project is divided up into 3 categories. We've got the project setup category, a model category, and a post-processing category. And the workflow that we have to follow for building the project, solving it, and post-processing is basically the exact same workflow that our consultants follow, but you just follow the workflow from top to bottom. So the first thing we do under the project setup category is set up our in-situ stresses. So I'm going to be configuring the in-situ stress. We can define the in-situ stress in 2 types. We can either assume we've got lithostatic degree stresses applying to this pit, basically gravitational loading with a K ratio in the X and Y direction, horizontal stresses as a function of the vertical stress. Or you can enter it in terms of principal stresses, where you enter the magnitudes and directions of the principal stresses. For this example, I'll be using the lithostatic stress, and I will just quickly bring up the stress state for this particular mine, and I'll just drag it over there. So these are the settings that we want to use here. So the azimuth of one of the horizontal stresses are 45 degrees, and we'll be using a K ratio of 1.5 in the X and Y direction. So let's go ahead, enter those. So 1.5 and also 1.5. Done. And so we've just set the in-situ stresses. The next step is to specify the mining sequence. Effectively, we want to link a mining step to each one of these geometries that we've just imported. So as we can see, we've got 5 mining steps, starting at step 1, ending at step 5. So I'm going to manually add 5 steps, starting at step 1, total of 5 steps. The start date representing the first mining step. So I'll just select an arbitrary date, 1 January 2025, and then assume that each subsequent step represents an annual interval. So I'll do that and select OK. We can see the first step that was created started at 1st of January 2025 as I selected, and then each subsequent step, then an annual interval from then. If I expand any one of these, we can see I've got two folders for pit shell, one for pit shell, one for water table, and then I've got two additional items: a generated pit shell item, just make this a little bit bigger, and a generated water table item. Our job as modelers would be to assign each geometry into each one of these folders. So I will typically would copy the first pit shell into the step 1 pit shell folder and do the same for the water table. Select the first water table, copy it, and paste it into the first water table item. And then at the point at which iMat builds the model, it basically regenerates. Based on the information that we dumped into these folders, it will regenerate the pit shell and water tables. It will produce new wireframes, cleaning up all of these artifacts, as I mentioned, these holes and these funny items that we've got here. It applies a new surface that will extend quite larger all the way to the domain boundaries, and you'll see what that looks like in a second. So just bear with me for a few minutes. Now you can imagine that if we, for example, have 100 mining steps, to copy all of these items one by one into each step, it can take some time. However, there's some ways that we can automate this. So one rule that iMat's got built in is that if your file name has got a number anywhere in the file name that can be successfully parsed, that number will then be assumed to belong to a certain mining step, and it can be automatically assigned. So I'll show you how that works. I'll right click on my mining sequence, say import geometries from the geometries plugin. I will import all 5 pit shells and say OK. And then I need to choose what geometry kind this is that I'm importing, and I'll select pit shells. So these are pit shells that I'm importing. And now the output window for each stage shows whether or not it could assign that specific geometry to a stage. So if I randomly just select one, let's say step 3, and look at its pit shells folder, you can see that iMat's successfully assigned the pit shell for step 3 to the mining step 3. Now, if I look at the water table, those I still haven't imported, so I need to do the same thing. I'm going to right click, import from geometries plugin. This time, I'm going to select all the water table geometries and OK. And then same story, it's asking me to choose the kind of geometry. I'll select the water table and OK. And now you can see water table, the geometry for water table step 3 was automatically imported. Great, so we've just defined our mining sequence. The next step is to define a pit region. But actually, before I get to that point, if I select any one of these mining steps, in the settings window or the properties window on the right-hand side, you can choose whether or not you want to include that particular mining step or do factor of safety analysis for that particular mining step. By default, the final mining stage, factor of safety analysis is turned on only for the final mining stage. You can override that by doing it for every mining stage if you like. The reason why it's not turned on for every mining stage is because it actually takes some time to do factor of safety analysis, as the model needs to be resolved several times for each mining step if you want to do factor of safety analysis for that step. Hence why only the final mining stage or factor of safety analysis is on by default. Great. You also have the option to turn factor of safety analysis off completely. So you can turn it off and then no factor of safety analysis will be done for any one of these stages. And then the model should solve fairly quickly. All right, so let's move on to the next step. The next step in our workflow is to define a pit region. So if I turn the pit region on, you won't see anything by default. And what I'm going to do is I'm just going to select the center X coordinate of my pit region and put it somewhere inside my pit shell. We see a plane appearing that's smaller than our pit. And what I'll do next is I'm going to create, or basically expand this plane such that it covers basically the entire footprint of this pit. Something like this. And next step, I'm going to go into a plan view and I'm going to digitize the boundaries of my pit. creating a volume that encloses the entire final stage of my pit shell. There we go. So that looks about good. And I might do is just shrink it slightly in this direction. We don't need it to be as large in this direction. And I'm just making sure that the entire pit geometry is covered by this pit region. Make it slightly larger in this direction. There we go. Now the reason why we're defining a pit region, so what I'll do is I'm going to turn on the entire free surface. This is to basically speed up the entire solving process and building process in iMat and Flag3D. What we're doing with this pit region is telling both iMat and Flag3D where our most important area is within this entire region that we want to include in our model. So one example is if we want to do factor of safety analysis, factor of safety will only be done for the zones or elements that exist within this pit region. Another reason is in our next step, we are going to define a model domain. By defining the pit region, we effectively tell iMat what the extent of our domain is when we calculate that domain. So I'll show you what that looks like. Let me hide the first step or the first pit shell and go on to the next step in our workflow, defining the model domain. This is basically a box covering the area that we want to include in our numerical model. We can do it manually, or we can select this button to automatically update the domain for us. And if we've defined the pit region successfully, the model domain uses the pit region and focuses around the pit region with some preset distance in the X, Y, and Z directions to define the extent of the domain. So this looks quite good. Now again, if I turn the first pit shell on, we can see that the model domain actually is significantly smaller than this entire area that we focus on. What it also does is it automatically creates the refinement levels for us. So let me just hide the domain. Or turn it back on. Apologies for that. So what happens is, or typically what we want when you do modeling is we create large elements or large zones far away from our area of interest, which is our pit region, and we want to create finer or refinements as we go closer to this pit region. So in this example, we're going to start off with 80-meter zone sizes far from our pit, and then iMat automatically going to refine the grid down to 5 meters close to our pit boundaries or our pit shells. Okay, so we've just completed this third last step in our workflow for building the model. Next step is to define the material properties. So by default, we have to have a host rock material, and then you can have as many sub-materials as you like. So if you have structures intersecting this is where you can add those structures. To keep things simple for this example, I'm not going to add structures in this example. I'm just going to add 2 material properties. First, assuming my host rock exists within an elastic material, and you'll see why I do that in a moment. So I just want to have a look at the elastic material properties. So we're going to assume a Young's modulus of 6 gigapascal Poisson ratio of 0.25. and a density of 2,600 kilograms per cubic meters. So I'll change my Young's modulus to 6, Poisson ratio to 0.25, and 2,600 for my density. Then I'm going to add a new subdomain, or basically a new material domain, and I'll call this my pit material. And what I'm going to do is use the exact same pit region that we've defined previously over here, and change only the material inside the pit region to be a hook brown material. Now, you may ask, why am I doing that? Well, one good reason is that if I only assume a plastic material inside this region here, the model will solve significantly faster. So having an elastic material outside the rest, and we're not really interested in the results outside. Only allowing for a plastic material inside the split region will speed up solving significantly, as typically what often happens for those of you that are experienced modelers, we get a lot of plasticity on the boundaries of our domain. So if I were to make this entire domain a hook brown material and allow for some plasticity, we get a lot of failures on the boundaries of the domain that slows down the solving. So this is one trick or one hack that you can do. Basically turn the rest or the outside material into elastic material and only focus in the area of interest around the pit and change that into a plastic material. Okay, let me just turn that off. So I've created this pit submaterial. I'm going to change that into a hook brown material, and I'll just bring this window across again just so you can see what the material properties that we want to assign. So the elastic properties for that hook brown material remains the same, but our GSI, MI, and UCSI, these are those values. So I'm just going to enter those. So GSI of 50, MI of 13, and UCSI of 20. Let's just see, and the tensile strength will leave 0. Great. So I've just defined my two material properties. And then the final step in our workflow is to define basically, well, the water density. And for this example, we can just leave it default. We don't want to change the fluid density of our materials. Note that when we created the Flag 3D project, we had, if we chose the option depth below surface or fixed elevation for our water table, this would those options, or basically those elevations properties, would become available here, where you can override those and choose those elevations or distance below surface. Great. So I've just followed the entire process for building the model or setting up the model, and I'm almost at the step where I can start solving. So I'm going to build a grid next, do a few sanity checks, submit it to Flag 3D for solving, and then we're going to come back and do some post-processing. So we're now over to the second phase of our model, is building the grid. So I'm going to select the right click on the grid, use the build grid option, and then you'll see that there's 4 steps that we need to do. First step is reconstruct the pit shells and water tables. Earlier on, I mentioned that iMat's got automatic algorithms built in to basically remodel all those nasty wireframes that we have for the pit shells and water tables, and it will produce basically good quality, was ensuring intersection with the domain boundary. Then step 2 is construct the octree grid. iMat built an octree grid of octree style grid of this model. Then apply material properties to each zone in the model, and then finally apply a mining sequence. So this shouldn't take too long. It should only take a couple of minutes, and I'll start the process. So it's doing step 1, reconstructing all those pit shells and water tables, and it's mostly done. So actually, let's have a look at what the output of that is while it continues with the rest of the steps. So show you what that looks like. So there's my pit shell for step 5. If I go back into my mining sequence, or actually what I'll do first is turn on my domain. You can see it's a problem. The pit shell doesn't extend all the way to the domain boundaries. So I go into my mining sequence for step 5 and turn on the generated pit shell item. This is what the new pit shell looks like for stage 5. So as you can see, where we've got blue overlap, that's where the original geometry is, and then these are all the holes that were automatically filled in. And using the mountain range, or basically the first free surface wireframe, we can see it extends all the way nicely to the domain boundaries. This is actually quite nice. Now, if we look at the generated water table for that stage, you can see the water table actually locates, well, first of all, it was extended all the way to the domain boundaries. Just bear with me for 1 sec. It's just finished step 2, iMat. So it's saying that we've got 3.3 million zones and 3.7 million grid points. Do I want to continue? I'll say yes, because I'm quite certain that this will solve on my laptop. If this were to be about, let's say, 10 to 10 to 20 million zones or even more. I know I won't be able to solve that on my laptop, so I've got the option to say no here and change some of my refinements, but I'll say yes and continue. Just get back to the water table. There's often a case that exists where we import water table geometries and it intersects the pit or even goes through the middle of the pit. So iMat ensures that, or it automatically detects when it reconstructs these wireframes if the water table intersects the pit or not, and if it sort of goes through the pit in the sense that we have free water inside the pit. That can be problematic, well, in terms of a numerical solving problems. It can be problematic if we've got free water inside the pit. So the algorithm that generated these two pit shells and water tables ensures that the water table actually never intersects the pit in such a way that we've got free water inside the pit. So that's also something that you don't have to worry about anymore when you do these models, is that the generated water table wireframes will never intersect the pit in such a way that you've got free water inside the pit. Okay, so it's nearly done solving or building the grid. It's actually, let's just have a look here. It's doing step 3. So it did step 3 there. It's assigned material properties to the grid. And then it went over onto step 4, doing the mining stages. And it's currently at step 3 out of 5. So we'll just let it finish. It should only take a few more seconds, or it's actually taking about approximately 23 seconds per step. So let's say probably another minute, and then the grid will be finished building, and then we can do a few sanity checks and then submit it to Flag3D for solving. There we go. So it's finished step 5. Now it's just saving the grid. It completed the process in just over 4 minutes. All right, so let's hide all of these geometries quickly, and we can still leave our domain on, and we'll just have a look at our refinements. So I'm going to first look at where the areas in my grid is that was refined down to 5 meters, and make sure that I've got the refinements around my pit shells that I wanted. So I can see all these zones are refined down to 5 meters. Just having a look at my final pit shell shape. It actually looks quite good. Let's just turn this off again. Yep, so it looked like it did a proper job. It refined down to 5 meters around my pit shells. I'll just turn the 10-meter refinements on, as well as the 20. You can see those are the zones that will have 20-meter cell sizes or zone sizes, 40 meters, and then obviously the rest is 80. What I'll also do is just turn on a cut plane that cuts through the grid. You can sort of get an idea of what the refinements look like. Again, just turn on my final pit shell shape, and then maybe just move my cut plane somewhere over there. Apologies, just move that back over there. Okay, so I'm happy with that. So I'll hide my cut plane. Also just want to have a look at my material properties. So remember, we created a hook brown material in my pit shell region. If I just render these quickly as faces and turn on my pit region volume, just to get an idea of where my hook brown material will be, and the rest all being elastic. So that's the hook brown material inside there, and I'm happy with that. Also, let's just hide the pit region. I'll do 2 more sanity checks. I would just one for my, let's say, mining step 3. I'm just going to randomly select a mining step and look at pore pressures for my water table if it was assigned correctly. So that's for step 3. And if I turn on the generated pit shell for step 3, or sorry, generated water table for step 3, you can see there's a water table. Those are the pore pressures that were assigned, so I'm happy with those. And final stage is just look for at stage 5 at which zones were identified as factor of safety zones, and those are the gray pixels that were identified here. So I'm happy with the output, and I'm ready to submit this to Flag3D for solving. So let's just turn everything off. To solve is actually quite simple. We simply click on this play button over here. The iMat detects that Flat3D is installed on my computer, or Flat3D user interface is installed on my computer, and will know whether I want to use the user interface version of Flat3D to solve this project. And selecting now will basically use the bundled version of Flat3D that's installed with iMat. And as of current, basically iMat bundles Flat3D console version 9.3.25. But if you've got an older version installed, you can use the user interface version of Flat3D. I'm going to say yes and start the UI version of Flat3D. And the way that iMat talks to Flat3D is by via these data files that automatically gets generated based on your input. So just having a look at the length of this data file, there's approximately almost 500 lines of code that's automatically generated for you. So for those of you that are established modelers, you'll be familiar with Fish. This is all the code that you would have to write yourself if you were to build all of this by hand manually. Now you don't have to anymore. iMat builds all of this for you automatically based on your selection. So just to show you what I mean based on your selection in the UI. So there's a Fish function that defines material properties based on what I entered on iMat, and all of these values are what I've entered earlier on in our workflow. And the same for in situ stresses. Let me just find that function. So there's an in situ stress function based on my lithostatic stresses, adding gravitational load with the different K ratios. This is all auto-generated for you. So what I'm going to do now is just get Flat3D to start solving this, and I will pause the recording. I think this will probably take about 2 hours to solve. I'll pause the recording and then restart the recording once the model's finished solving. So I'll go ahead, I'll click the run button in Flat3D and get Flat3D to start solving this. All right, so our model just finished solving. It solved all 5 mining steps in our sequence, and we are ready to do some post-processing. So we're going over into the third category of our workflow. Now, there's many different ways that we can do post-processing, create contours, or even create movies within iMat. I'm not going to be able to cover every single item in the post-processing for the session, and we would be happy to have a chat to any one of you and show you some of these features later on. But I will be using some of the features that exist today to show you basically some pretty pictures. Okay, so the first thing we can do is, for those of you that are familiar with Flat3D, is just use a basic cut plane to cut through our grid and look at different modeling parameters. So I'll turn on my cut plane, and we've actually used this earlier on during the session to look at pore pressure for a specific step. So I've got step 5 currently set as my active mining step. So we're going to look at the pore pressure that's assigned to our model for step 5. But at the same time, we can look at any other modeling parameter as well. So in this example, I'm selecting sigma 1 now. And what I might do as well is just hide my mined out zones, so we can actually have a look at the values below the pit. We can move this cut plane with either the controls option, or we can manually move it. So I might actually just translate it slightly to the middle of my pit and have a look at what that looks like. Next thing that I can do is I can turn on ISO surfaces for certain parameters. So let's just look at ISO surfaces of sigma 1. We'll just let this finish building. So actually, we've got 10 different levels, different ISO surfaces. This sort of makes sense to the stress distribution for lithostatic stress field. Or if I turn on ISO surfaces of pore pressure, just so you can get an idea of what that looks like. So remembering our water table was down here and looking at the different ISO surfaces for the pore pressure, you can see how the pore pressure actually changed due to the pit being in this region. Great. So that's the isosurface option. There's another option where we can interpolate certain parameters onto the pit shell. And I guess one of the more important parameters that we typically want to look at is displacement on the pit shell. So what I'm going to do now is look at the displacement interpolated onto the generated pit shell for step 5. So those are contours of displacement. You can do the same for as with the cut plane. Choose any modeling parameter that you like, maybe some shear stress magnitude interpolated onto the pit shell, but it works similar to the cut plane. What we can also do is look at, remember we did a factor of safety analysis for step 5, so we can look at the factor of safety for that final mining stage. So looking at the legend here on the left hand side, we can see that there's an area of the pit where the factor of safety is less than 1. Majority, we actually have a factor of safety of 1.5 or greater, but we've got these areas where the slope actually failed. Well, that has a factor of safety less than 1. And again, you'll notice that we don't have any factor of safety outside our predefined pit region. The reason behind the pit region is to speed up the entire solving process. So there's 2 more options. We can use the result points option and to do some post-processing as well as movies. So one option that we can do is take some of these structures. There's a main fault that sort of cuts through the pit. Let me just turn on the final pit shell stage again. So you can see it sort of cuts through the pit over there. What we can do is we can copy this main fault, paste it into our result points folder, and then interpolate stress displacement and plastic strains onto the pit shell for a few mining stages. So I'll select stages 4 and 5, and we'll do that interpolation, and we'll calculate some modeling parameters on this fault. So we've just finished doing the interpolation, and now I'm going to select a parameter, let's say for argument's sake, the shear stress magnitude, and turn that on. You can see the shear stress magnitude interpolated onto this fault. We can choose maybe, keeping in mind that a big majority of our model was elastic, so a nice parameter might be a parameter such as excess shear stress. And excess shear stress, we usually interested in values just larger than 0. So I'm just going to change my color range to look at values larger than 0. And choose that into a step. So those are all ESS values larger than 0. So with the result points, you can dump in as many wireframes or as many geometries as you like into this folder here, and you can interpolate for any stage stresses, displacements, and strains onto those wireframes, and then render effectively any modeling parameter. Finally, we've got the movies option. Now, I'm not going to cover the movies option or show you how to generate a movie today. But the idea of the movies option is if we, for example, have 100 mining stages and we want to look at different areas of our mine and create various contours for different modeling parameters at those different areas, it will take a significant amount of time to do it manually. The idea with the movies option is that you set up these movies, generate it overnight, and have access to the images that created these movies, and then be able to batch reprocess all the results in basically one quick go the next morning when it's finished generating. So you can do batch post-processing using the movies option here in the post-processing category. Okay, I think I might end the recording there. We'll be available for questions if you've got any. I hope you've liked this presentation. Thank you very much.